How are you? Everybody good? Really, really great to be back in Taipei. And it's fantastic to see all of you here. And I'm really honored that we were asked to present here. So my name is Markku Lepistö. That's a funny name because I'm from Finland. I'm Finnish. Can you stretch the screen a little bit? It's a little bit out. Can you move the screen a bit? So my role at Amazon Web Services is a technology evangelist. So what is a technology evangelist? Well, I'm a techie. Okay, I'm a geek. I admit it. I love technology, and I love showing technology to people who are interested. I hope you are. And that's what I would like to do today. So today's topic is smart devices. Can you squish the screen a little bit, please? It's out of the screen. Sorry, let me just very briefly check the display setting. That's fine. Squish, 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 squish. All right, as they do it, let's move it along. So smart devices, that's the topic for today. What are these smart devices? What are these devices that we are talking about? Well, as you have seen already earlier, there are many kinds of devices. There's a fridge that's hiding behind the corner now. It doesn't want to be seen. There are wearables like the Misfit Shine that I love that I'm wearing here. There are all kinds of drones and robots that are flying around or roaming around the countryside. And many of them are actually powered by this new generation of open source hardware that has really enabled building these kind of devices, like the Raspberry Pi and the Arduinos. So we have a lot of devices. But maybe the question is, are they smart? Well, let's take a look. Let's take a look at a couple of the typical devices used to actually build these smart devices. So first we have the Arduino. The Arduino Duo has a 20 megahertz CPU, which is 8 bits. It has 2 kilobytes of memory and 32 kilobytes of storage. So the Arduino is roughly the power of a 1970s computer. It's not that powerful, but I love it. I have 3 of those. And then we have the Raspberry Pi and the BeagleBone, which are much more powerful. They are already proper computers. Let's say that they are maybe like a laptop a few years ago. But it's not really that powerful. So they are not really that powerful as computers. They are devices. But they have some really interesting properties. They let us do really nice things, like this. You can connect devices, you can connect sensors into these little boards. For example, you can put cameras, microphones, GPS devices, gyroscopes, accelerometers to act as the eyes and the ears and the sense of balance. You can connect all kinds of motors, manipulators, actuators, relays, and switches for these devices to control the physical objects. You can put wheels on them, you can put propellers, you can even put rotors so that they can move around and maybe fly around over your head, hopefully not crashing. So the devices are great at interacting with the real world. But there are some challenges. Let's take a look at some of the challenges. Well, you might easily have thousands of these devices. It could be a sensor grid that you have deployed all over Taiwan. There could be some devices you're selling to your customers that are smart, that are connected to the internet. Like Samsung TVs, for example, you might have millions of these devices connected and producing data. On the other side, you have your customers. So again, if you, for example, sell 1 million TVs, or you have 1 million sensors, they're producing a lot of data, then you have a lot of consumers or customers who want access to the data. So millions times millions. So by definition, we are talking about distributed systems at massive scale. So we have some challenges there. So Internet of Things, many of them, and the cloud. What can the cloud bring to this picture? Well, the cloud can bring utility computing. Basically, very low cost, readily available, on demand, pay-per-use, unlimited storage capacity. Unlimited. Unlimited compute capacity. So what do you get when you have unlimited storage, which is kind of like memory, and unlimited compute, which is kind of like logic processing? You get the brain. So the cloud can bring the brain to the picture. So now we can complement the picture. Millions of devices connected to the cloud. They are like sensor networks with a neural system connected to a central brain that can analyze the data coming in and give control feedback instructions back to those connected devices. So then we get smart devices powered by the cloud. Let's take a look at some of the examples. Here we have an Illumina DNA sequencer. It reads the DNA samples, but it would be really expensive to build a supercomputer inside the box for every one of those boxes. So it's simply reading the DNA sample, uploads the data to the cloud, where the massive capacity is used to process, sequence the DNA, and the results come back. And of course, the results are kept in the cloud in durable storage. Then we have Tata Trucks. Tata is running 200,000 trucks in India. They do preventive maintenance by equipping those trucks with sensors that are uploading data to the cloud, and they can do predictive maintenance, preventive maintenance to see that this truck is about to break, and they bring it to service before it breaks down on the road and causes a business disruption. Shell is, for example, dropping a lot of sensors into the oil well, sensor metering who knows what, but they are telling Shell basically where to drill. And then we have General Electric, like you saw earlier, building artificial intelligence in the cloud, optimizing the parameters of their turbines and engines. And then we have, for example, the ocean. There are a lot of sensors in the ocean, which is nice for climate prediction, seeing the temperature, seeing the ocean currents, tens of thousands of sensors in the ocean. And the scientists basically have now 10 gigabit internet connections connecting directly to the Amazon data centers, where the data is uploaded. They can analyze the data. They are no longer limited by lack of capacity for storage. The data is already there, and they are not limited by capacity for compute and processing. They can simply spin up any kind of analytics jobs they need to do massive distributed analytics. And it's not just here on Earth. Let's see how our friends at NASA JPL are doing Internet of Things on other planets. Volume.
Take a few moments to learn how, in just 60 minutes, NASA can process a day's worth of new discoveries from the Mars Science Laboratory. The red plains and pink sky of Mars hint that volcanoes, meteors, and flash floods once shaped the landscape. Today, a number of robots, sent by NASA's Jet Propulsion Laboratory, explore the atmosphere and surface of Mars. These rovers are on a quest to find out whether the red planet is, or ever was, an environment able to support life. However, giving instructions to a Mars rover is more difficult than most people realize. Unfortunately, there's no joystick controller a scientist can use to move the rover around. And even at the speed of light, it still takes between 7 and 20 minutes for a transmission to go from Earth, across space, to the rover on Mars. To make matters even more complicated, there are only short periods of time in which scientists can communicate with the rover at all. This makes for a precious window of time in which NASA JPL engineers must determine the next day's mission for the rover. Sometimes they have just a few hours to download data from the rover, then process and interpret that data in order to send new mission instructions back to Mars. When they can speed up the analysis of the data, it leaves more time for science. That's why the team uses Amazon Web Services to spin up hundreds of Intel Xeon E5 processors when they're needed. With the scale and performance of this on-demand computational cluster, NASA JPL engineers are able to drive 12 teraflops of performance for less than $40 an hour. This leaves more time to work on programming Curiosity's next steps. It also enables NASA to get greater utilization of the rover's unique capabilities. Closer to home, NASA JPL scientists also use Amazon Web Services and Intel Xeon E5 processors for other computationally intensive workloads, such as robotic articulation calculations and Arctic climate analysis, all while enabling their researchers to work more productively and cost-effectively. When the team needs more computational power to support these and many other missions, they can easily provision what they need as and when they need it. This on-demand scalability lets NASA scientists and engineers keep their focus on exploring the Earth, the solar system, and the universe beyond.
Excellent. Go Curiosity. All right. So that was an example of Internet of Things on other planets. And then the Climate Corporation. You already heard today they are doing basically weather predictive analytics, and they're providing insurance to farmers, because if the weather changes, it will impact their crops. And in order to do this analytics, they need a lot of data points. How many data points? Well, they are collecting, for example, 150 billion soil observations, humidity, temperature, etc., and then all these normal weather measurements, and they mash it all up together. They're storing hundreds of terabytes of storage in Amazon S3, a simple storage service, and then to do the analytics, basically they're running simulations where they have over 5 trillion data points. And in order to run these simulations within a reasonable time, they are spinning up Hadoop clusters for massively parallel analytics in the cloud with 5,000 to 6,000 nodes in these Hadoop clusters. And after the job is done, they can throw away those disposable infrastructure and only pay for what they use. So simulations. Remember, if you build an Internet of Things system, you might have millions of things, and you might have millions of customers. You have massive scale. How do you know that you're able to handle this scale? Well, easy. You can just simulate your devices with Amazon EC2 virtual machines, so we call them instances, and then your customer load you can also simulate using EC2 instances or servers in the cloud. You can have one instance to basically develop your script, make sure that it works. Then you pump up the system to 1,000 instances, for example. When the job is done, you go back to one instance or 0. And remember, in the real cloud, when you switch off the resources, the bill goes to 0. If you buy 1,000 servers, first you have to figure out where do I put them, who's going to install them, and then you're stuck with them for 3 to 5 years depreciating in your books. But your business needs are changing, so you have variable needs. You may need new capacity right now to try something new. And when the experiment is over, you throw them away, and the bill goes to 0. So the cloud provides utility computing like electricity today. Enough of the slides. This is an Internet of Things Cloud and Big Data conference, so I was thinking, let's actually do something real. I'm going to show you a demo where I'm going to use the Arduino Yun, which means cloud, as I'm sure most of you know here in Taipei. And I'm going to use a Raspberry Pi. And I'm going to do this. I have an Arduino with an accelerometer connected, like a G-force meter. It will be streaming data, the sensor readings, using MQTT protocol, which is a lightweight messaging protocol specifically designed for Internet of Things. It's going to be streaming the data to the Raspberry Pi, which is running Mosquito. Can't pronounce it, Mosquito. MQTT broker. It has the AWS SDKs installed. So once the data reaches the Raspberry Pi, it's going to be streamed up to the Amazon Kinesis service. What is Kinesis? Kinesis democratizes real-time data analytics. It's a fully managed service in the AWS cloud where you can stream data from hundreds of thousands of data sources up to terabytes per hour. No commitment and pay-per-use. So we will be streaming the data from the accelerometer through the Raspberry Pi to Kinesis, and then we will also be updating some records in Amazon DynamoDB, which is a really cool database service. It's NoSQL, it's provisioned throughput, and it's guaranteed quick response time. And it's zero maintenance. You don't have to install a database. You just provision tables and indexes, and you provision a throughput. And you can change the throughput as your business needs change. And it's also unlimited capacity. So nice. Kinesis and DynamoDB will be receiving the data, and then using Amazon AWS Elastic Beanstalk, we have a web dashboard basically showing them the sensor reading as a user interface. So let's take a look. First, I'm going to show you the hardware. Now somebody's thinking, really? Amazon Web Services is presenting, and they are showing hardware on stage. This is new. So, there you are. There's my Arduino. This is the sensor. This is the accelerometer. Yeah. Guess it's something like what we have in our phones. So that's my Internet of Things thing. And then for the MQTT broker and uploading the data to AWS, I have a Raspberry Pi. Yeah, so devices. And here, I'm going to be switching to the Amazon Kinesis console. This is now live. No recordings, no screenshots. Here we have the console for Amazon Kinesis. So Amazon Kinesis, you can provision streams. A stream is an endpoint where you start pumping your data into. You provision the capacity and throughput of streams. Here I have provisioned just one shard, which gives me 1 megabyte per second or 1,000 messages per second throughput. It's quite enough for this little Arduino. You can see that my system is now pumping some data into this Amazon Kinesis stream, so we can see some statistics. And here, we have the actual graph. Just refresh the page, and what we can do is I show you that as I move the accelerometer around, the readings change, and then the graph will update. So on the top right there, you see the G forces. So now I'm introducing quite a lot of G by tilting this accelerometer. Let me tilt the other way. Oh, negative G. There you go. Back to positive G. Negative G, and there you go. As you can see, the sensor graph is now reacting. So the little Arduino here is reading the accelerometer as I'm now throwing it around. It's using MQTT to post the packets to the Raspberry Pi, which is Mosquito, receiving the packets, and then using the AWS SDKs, it's pumping the data up into Kinesis. You can see that on the bottom right there. And then the graph is just reading from Kinesis the latest numbers. And then we're also updating a DynamoDB table, basically for the graph to know the pointer, what are the latest records that it has handled. So it's just handling some pointers in the stream. There you go. Internet of Things, not just slides. And AWS with hardware on the stage. This is weird. So, that's one sensor. That's one Internet of Things, or two if you count both of these devices here. It's not terribly big data, is it? I mean, the data amount here is quite reasonable. It's quite small. But the beauty of these cloud-based big data services is that, first of all, you don't have to buy the backend hardware. So now I'm running analytics in the cloud. I'm doing real-time streaming data analytics. True, I have one device, quite little data coming in. But the cloud services are scalable. So as I then go into production, I start shipping thousands, even millions of these devices. The capacity is going to go through the roof. With these cloud services in the backend, you don't have to buy hardware to support that number of devices and customers, and they scale from this one device to hundreds of thousands or millions of devices. You don't have to re-architect your system. The same exact system will work even if there's 1 million devices there. And it's pay-per-use like electricity, so when your business needs go down, you pay less. Then, I mentioned simulating 1,000 servers. Well, here we are running 1,000 servers. Let me zoom in a little bit so you can see better. So I have one real device here, the Arduino, sending accelerometer data to Amazon Kinesis. And I mentioned that before you go into production, you probably want to test that your thousands of devices, or even millions of devices, that you can handle the system load. So I have spun up, or deployed, or provisioned 1,000 servers in EC2. So I'm running now 1,000 servers. They are the humble micro instances, which are handy for simulating, for example, Raspberry Pis and Arduinos. So with these 1,000 instances, you can easily test the load, simulating all these devices, or your customers. And here in Kinesis, I actually have a second stream. So the second Kinesis stream that I have is now receiving data from these 1,000 simulators in EC2. They are now pumping something like 100,000 requests per second, so significantly higher load than that one single Arduino. So this is just demonstrating that the backend services in the cloud are scalable. Doesn't really matter how much data you're pumping in. So this is our demo system. We used an Arduino, we used a Raspberry Pi, Amazon Kinesis, DynamoDB NoSQL database service, and then Elastic Beanstalk is showing the graph as a web dashboard. So that was the demo. Hope you enjoyed it. Now you might be asking yourself, okay, he actually deployed 1,000 servers in Amazon EC2. How much? Well, I used something called the spot instances. There's something interesting in EC2. We have on-demand instances, which are the kind of normal ones with a regular hourly price. We have reserved instances. If you know that you need to be running certain workloads for most of the time or all of the time, you can get a significant discount on the hourly price using reserved instances. Then there's a third option, spot instances. Basically, for the excess capacity in the Amazon cloud, regions and data centers, we have a spot market. You can think of it as a stock market with laws of supply and demand. You name the price for compute. You name the price, what you're willing to pay for this compute capacity, and if the laws of supply and demand, fluctuation in the spot market, mean that the price is right, you get to run the instances at that price. If, however, the price fluctuates higher than you're willing to pay, then we take those instances away from you. Not the best for running databases, for example, but fantastic for doing simulations, DNA sequencing, etc., things at scale. Currently, in the US East region that I was using, the spot price fluctuation is between $0.0031 per hour to $0.01 per hour for those micro instances. And I ran 1,000 of those. $3 to $10. So using the micro instances, using the EC2 spot market, you can run 1,000 servers for $10 an hour. Not too bad, versus buying those servers. And then, in our demo, we used a couple of the services in the AWS Big Data portfolio. We have a comprehensive portfolio of big data services, ranging from collecting the data into the system to storing it in services like Amazon S3 with 11 nines of durability, unlimited storage capacity, analyzing the data with Hadoop, for example, Elastic MapReduce, simply deploying Hadoop clusters, fully automated, our Redshift data warehouse, columnar, petabyte scale, fully managed, less than $1,000 per terabyte per year. Kinesis, you saw, real-time streaming data analytics. And then, of course, you need to share the results, you need to visualize so that your business benefits from these analytics. All of these services we are providing out of our global regions with our availability zones that have clusters of data centers and 51 edge locations. We have 10 regions around the world. Here in Asia, we have the regions near Singapore, Beijing, Tokyo, and Sydney, Australia. So leveraging the cloud and these tiny little devices that I really love, you can make smart devices that are powered by the cloud that add value to your sensor grid or physical devices. Thank you very much. See you, Niman.